Howdy folks, this is Gabriel Signs again in with the Intro to Psychology, Chapter 5, Sensation and Perception. I've put in a lot of things this week for you to sense and perceive, starting off with this little weird image. So we've got two pictures here, one that's regular with a guy and a lady in the background, and on this right hand picture we've just taken this lady in the background and popped her down here by the dude's feet. Now obviously the lady is not this size, but the weird thing is that her size looks teeny tiny compared to her size over here, which looks much bigger. If you take your fingers, you'll be able to check. They are actually the exact same size image, but because this guy is right next to her, the relative differences between this guy and this guy over here instead make this lady appear super small. And we'll actually see a number of illusions and things kind of like that throughout the semester, throughout the chapter, and you'll have an opportunity to learn about how a lot of these sorts of illusions work. So let's get started. I'll have a lot of these pause moments in the video so that you can pause and look at things on your own and think about them. So let's get started here with I actually going backwards in the PowerPoint slides to take a look at an interesting photo. Now, the thing about this photo is that at first glance it is not remarkable at all. However, if you look a little bit more carefully, you'll start to notice weird things. So I'm just going to go ahead and pop over there in 3, 2, 1. Oops. Okay, so what are you starting to notice here? What's going on? Go ahead and pause the video here and take a careful look. 3, 2, 1. Okay, so if I skip to the next slide, in a moment I'm going to show you all the mistakes that I'm aware of. So make sure you've had that chance to pause. Okay. So I've got a lot of mistakes in this image, and I've gone ahead and circled as many as I could personally find, as well as the ones that other people have pointed out for me. Part of the reason that you don't necessarily perceive things immediately, even though they're right there, is because a lot of our perceptions are based entirely on our conception of what we're going to see. And so the immediate visualization of this is a diner would fill our minds with a lot of assumptions on what's supposed to happen. And as we look more carefully, we slowly start to see things that are in the diner, but they really shouldn't be. So let's go ahead and start the chapter. This week we're going to take a look at 4 different parts of information. First, the information processing, basically how do we work with information, and our perceptions. Second will be sensations as relative information. Third, sight and sound. Finally, other senses. And these will make a lot more sense as we go on. To start, I've got a video here. This shows kind of what English sounds like to non-native English speakers, or sorry, to non-English speakers, so folks that don't understand English. You'll notice that there are some things that make sense to you as an English speaker, but also a number of things that are just gibberish, gobbledygook. And the reason this video is put together is to show you that other people perceive our language in the same way that you might perceive other languages as just weirdness. Because we're not able or used to processing certain sounds or pauses, certain types of inflection. We don't understand those other languages, and so that's the only thing we can hear, but they're the things that stand out the most. Because we understand English, we automatically process that information, and so we don't notice a lot of the things that kind of become super obvious from this video. So go ahead and give that a watch. I'll give you 3 seconds here to make that happen. Pause the video and make it happen. 3, 2, 1, go. Okay. Next up, we have our first vocabulary term. The first one is prosopagnosia. Sorry, I didn't give you a chance to try and say that out loud for yourself. Prosopagnosia is basically an inability to perceive faces and remember faces. It's not as though the faces are invisible, but they just don't quite make sense, just the same way that sometimes you might look at something for a moment and you don't really get it, and then after a second or two you do get it. So I'm going to give you 3 moments to click on this link and watch the video until you get to this part here. the military dudes. That's all that you have to watch, but if you'd like, feel free to watch the rest of it. Presumably this is from a 60-minute section, so it's a lot longer than you would be required to watch. So take that time now. 3, 2, 1. Okay, so both of these examples show you how our own minds play such a huge part in our ability to perceive and understand information. The reason we've presented them here is because sensation and perception are totally different ideas. Sensation is how our sensory receptors and nervous systems receive and represent stimuli, so kind of the biological aspect of receiving information. And then we also have perception, the process by which our brain makes sense of that information, turning it into meaningful objects and events. So kind of how does our mind use that information to give us our sense of understanding for the world, and how does sometimes we can sense things without really perceiving them accurately, and how sometimes our perceptions can lead us astray. So in those two examples, what we've got are sensations that are perfectly fine. Hearing a language I don't understand, or seeing faces that I don't understand. But our perceptions of them are skewed. First, because we don't understand the language, and second, because there's some neurological issue preventing us from understanding the faces. Next up, let's talk about hemispatial neglect. So hemispatial neglect is simply an inability to see one side of your vision. We've learned in previous chapters that vision is organized such that the left side of the vision is handled by the right side and vice versa, and that travels through parts of the midbrain, and that there's a need for the left and the right side of the brain to work with visual information, because the right side is better with visuals, but the left side is better with language. So you can imagine there are a number of reasons why a person would be unable to see part or half of the image. Go ahead and click on this video here. Try to watch till you get about to the point this image is at. And pay attention. See if you can think about what might cause that hemispatial neglect. I think they will mention it here, but what's going on is that the person is experiencing sensation. Their eyes can see it, but due to some neurological issue, their perception of the visual information is impaired. They won't be able to see the left side of the visual information. So another example where sensation works, but perception does not. I'll give you 3 seconds here to watch the video. 3, 2, 1. Okay, so let's get really into that information processing material. And then just to let you know, I do have a couple stars on some of these slides. That's a remnant. We're using these slides from a different class that I've taught in the past. Sorry about that. So information processing. To name what that is, it's just how do we work with information that we receive. And I've got one example of how we work with information here called bottom-up and top-down processing. Bottom-up processing is using your sensory information to understand the world around you, whereas top-down processing is really based around using your prior existing knowledge to understand the world around you. There's a video here that you can watch if you'd like another explanation and more examples of that. The example that I like to use is to talk about the big rubber dog. Sorry, it sounded as if someone was yelling. Anyway, so what is the big rubber dog? We've got here a picture of a rhino, and if it's the first time that you've seen a rhino, you may call it a big rubber dog because you're familiar with dogs. They have 4 legs and their heads are kind of down and the shape of their body look like that, and you're familiar with rubber because you've seen tires. And so you might say, well, the rhino you might call the rhino a big rubber dog because you haven't seen the rhino and you don't have a name for the rhino, but their skin kind of looks like rubber and their body structure kind of looks like a dog. In this case, you're using top-down processing and bottom-up processing to understand the world around you. You've never seen the rhino, so you use your existing knowledge about dogs and rubber to come up with a name for it, figure out kind of what it might be like. And you're using bottom-up processing to see the visual information and understand that it's something you've not seen before, but it does make some sort of sense. It's important to note that with bottom-up processing and top-down processing, you're never going to just use one of the two. Instead, you'll always kind of use both to understand visual information, and they'll meet somewhere in the middle. There are many situations where a person might use bottom-up processing or top-down processing more than the other one, though. Like, for example, a child would likely use bottom-up processing much more than an adult because they don't know as many things as adults do. Okay, so this slide kind of covers the stuff that I just verbally said, but as another example, and this is one of my most favorite examples, how come parents can find things in their kid's room that seems totally obvious? Well, imagine you're a kid and you've lost your shoes in your room, and it feels like mom can find your shoes really, really easily, even though you spend hours and hours looking for them. So why might that happen? One answer is that you are used to what your room looks like. You're used to where you normally put your shoes. And so if you put your shoes in a weird place, your bottom-up processing may prevent you from seeing them because you're not really looking for them there. Alternatively, your mom doesn't have any preconceptions of what your room looks like because she hates going in there. So when you ask her where your shoes are and she starts looking, she'll actually see your room exactly for what it is instead of what her preconceived notions tell her it should be. Because she's not used to looking in your room, she's not used to seeing the things in your room, and it's a lot easier to see things for what they are, so it's a lot easier for her to use that bottom-up processing to find your shoes wherever they happen to be. Okay, I've got a couple more examples about bottom-up to top-down processing. Take a moment, maybe pause the video, see if you can find the panda in this picture. 3, 2, 1. Finding the panda is hard because you know pandas are black and white, and this picture is mostly black and white. Our eyes are attracted to the colorful things on the snowman, but the panda doesn't have anything colorful to it. When you do find the panda, you'll notice that it's very, very difficult to stop looking at the panda. You go from bottom-up processing, really looking at the picture, to top-down processing. Well, now you know where the panda is, so you'll mostly just look at the picture in terms of your understanding that there is a panda in that picture. There's other things that you can do. For example, can you find the little bit of writing in the picture where the artist put his signature? Can you find the snowman with the red and yellow scarf? Once you've found one thing, it can be harder to find other things because of the top-down processing. Next up, do you know what this Pokemon is? It's one from the first generation, and I'm very familiar with it. It's called a Diglett. Now here's where the example might blow your mind. You can tell that this little dude's got a couple of eyeballs and a shiny nose, but think about it for a moment. Maybe it's not a nose. Maybe it's a mouth that's really open and he has one giant tooth. Can you unsee the information that I just presented to you? It's really hard to switch off of top-down processing sometimes, especially if you're specifically trying to. A lot of times you may lapse into bottom-up processing when you're just doing your day-to-day work. But top-down processing is what happens most of the time because your brain is lazy and efficient, and it would much rather assume it knows things than try and figure them out every time it gets information. Okay, we've got a couple more examples of bottom-up to top-down processing. Here, the FedEx sign actually has kind of a secret in there that may make you want to use FedEx a little bit more, may make you associate FedEx with logistics. If you haven't found it yet, there's an arrow in the image. If you can't find it, go ahead and pause the video, but I'm going to keep going. Next up, we've got the Tostitos logo. Can you find the cool image in the Tostitos logo? I think this one's a little bit more obvious, but you may not have noticed it until now, until we kind of pointed it out. Same thing with the logo for, this is for the Hunger Games Mockingjay. I don't know if you're familiar with that, if that's still cool, but the weird thing is that for me, what I see is an image of Johnny Bravo. Johnny Bravo is a cartoon from some time ago, and if you're not familiar with the Hunger Games, there's no way you'd be familiar with Johnny Bravo, but feel free to give both of them a look up. They're not bad. Next up, the Beats logo is actually designed to look like a person wearing Beats. You can actually see it much more easily once you draw on eyes and a mouth. Makes a lot more sense. There you go. I wonder if Beats are still popular. I'm not totally sure, but when I was putting together these visuals, I originally did that around the time Beats was a cool thing. So we're back to the panda image. Quick, don't look at the panda. Don't look at the panda. It's hard, right? It's hard to not look at the panda or even think about it because, well, first because I'm talking about it, but also because of that top-down processing, because your brain wants to think about the panda. It knows that that's the interesting thing about this image. Okay, let's get to some more sciencey type stuff. Absolute thresholds are the minimum level of information that your mind needs to perceive a difference. That's kind of weird and awkward, but it makes more sense if you talk about hearing tests. Go ahead and click on the link here at the bottom or type it into your browser and try the hearing test. The hearing test is designed to check your hearing. And so, more specifically, an absolute threshold is the minimum amount of stimulation that your mind needs to identify that there is a stimulation. So you need to be able to identify the stimulation at least 50% of the time. So be aware that at this minimum or absolute threshold, you won't always notice a thing, but if you notice it half of the time, it counts. Stimulus that is just below stimulus that is below your absolute threshold is considered subliminal, and you may notice it, you may not notice it. We'll talk more about subliminal information later on in the chapter. Okay, so here's difference threshold. Very similar to the absolute threshold, where absolute threshold was the minimum amount of information for you to detect any stimulus. A difference threshold is the minimum amount of difference for you to detect a difference. So not just is there something, but is there a difference between these two things? Part of the way people test this is by having people arrange blocks of colors by their color. So it's pretty obvious that there's, here we go from kind of this brownish to a green, and here we go from orange to a more redder orange, and over here we go from a darker purple to kind of a brighter pinkish reddish salmon. So do you think you can do this task? Are there some images or colors that seem like they're exactly the same? Turns out girls are better than boys at working with colors in this way, but everyone can learn this over time, and there are certain limitations on the minimum differences that people can identify. Bear in mind that there is no minimum difference between colors that exist in the real world. The colors have a continuous difference scale, so you can always make two colors that are increasingly similar to each other without being exactly the same. Does that make sense? I hope it does, because we're moving on. Okay, so this part is all about the relative nature of sensation. You'll see that through many examples. The first one here is from a video from some time ago about this dress that appears one set of colors for one set of people and another set of colors for another set of people. The reason for that, and they describe it in the video, is that your brain perceives the colors based off of what you think is going on in the image. They do a really good job of explaining that in the video. So please take a moment to watch the video, and I'll meet you back here in 3 seconds. So pause now. 3, 2, 1. Were you able to see the four different colors of this 2-color dress? It's kind of a funky, weird thing. I have a lot of trouble seeing the black and blue in this image. I always kind of see it as a gray and white, and there's just a really bright background. But I've been told that I'm wrong, so sorry about that. Next up, I've got another example here with a YouTube video. This is a really cool YouTube video because it shows you that there is no such thing as brown. In fact, the color brown is in truth dark orange, which is why you might realize that if you think about it, if you kind of close your eyes and imagine your color circles, you can make green by blue and yellow, and you can make purple with blue and red, and you can make orange with red and yellow. But how do you make brown? Turns out that you make orange and then you make it darker. We perceive brown based off of the relative difference between the orange and whatever context it's presented with. So go ahead and watch this video. It's a much longer video than what I'm looking for here, so you don't have to watch the whole thing, but he goes through an interesting explanation on how it works. And if you start earlier in the video, he talks about how different colors work in terms of different different visual color systems. So feel free to check this out. You don't have to check it out more than just the brown example, though. Okay, habituation. Habituation is our senses' ability to get tired of things. Habituation just means that over time, when you perceive something, you'll slowly perceive it less and less and less and less, especially sensations with strong stimulative abilities. Why? Well, if you hear a really, really loud noise, you don't need to hear that really, really loud noise all the time. If you smell something, you don't need to smell it all the time. And we've talked about how our neurons can get tired of things, and in the same way our senses can get tired of things. We'll actually see this in a couple of different ways, but the way habituation generally happens is through just an experiencing of the same stimulus over a long period of time, or a strong stimulus over a short period of time that makes us hear less. A good example of habituation is if you've ever been to a really loud place. You go to a club, music's really, really pumping, you go outside and you feel like your hearing's totally gone. It comes back after a period of time, but it makes sense that your sense of hearing would habituate to the really loud noise, because it doesn't need to hear the really loud noise all the time. Next up, sensitization. Sensitization is kind of the opposite of habituation. It's your ability to become sensitized to hear more information or to perceive more information from your senses than usual. Sensitization happens because it's beneficial sometimes for us to really pay attention to things. A good example of sensitization is if you're alone in a strange or spooky house, you might start to hear lots of spooky noises. And why that's happening is, well, you're scared and you're not used to hearing those noises. And so once you start getting scared, you'll start getting sensitized to the noises, and it's a little bit of a self-fulfilling prophecy, because the more you hear the noise, the more scared you get, the more noises you hear. Okay, so next up I've got priming. Priming is anything that affects how we perceive things. There's lots of different ways to prime people. I've got two videos here. Both of them are pretty interesting. I don't think that I would present the whole of both videos to the class, so I'd probably have the class pick one video. At the top left, it's kind of a magician tricking people into making a certain judgment. The bottom right comes from a British, I think they're both British. It comes from a television show where people make several different types of choices and participate in different types of studies and are affected by things differently based off the things that they're primed on. So this one is a little bit of many different examples. I think I'd likely show this video in class. This one is one longer term example, but it's also a little bit cooler. So go ahead and pick to watch at least this bottom right one, if not both. And I'll give you 3 seconds. 3, 2, 1. I hope you did find those videos interesting. I really, really enjoy them. I think they're lots of fun. Let's move on to subliminal messages. So you've probably heard of subliminal messages before. The idea that you can be influenced in your decision making and opinions via the information that's coming into your mind without your consent, by information that may be subtle so that it's hard for you to notice it, or information that is placed in front of you for just a really brief moment so you might not notice it consciously, but do you notice that information unconsciously? It turns out that subliminal messages don't really work on people. They can influence their decisions, they can change little things about them, just kind of in the ways that we saw in the previous set of videos, but they can't really change your decisions if you're really trying to make a careful decision. So this link here actually will tell you a little bit, this video will tell you a little bit about how the idea of subliminal messaging actually came from a fraudulent bit of research that some dude did to convince movie theaters that they could sell more popcorn based on his research. So go ahead, click that thing, see if it's interesting to you. This is not a really required video, but I think it's lots of fun. I think all the videos I put up here are interesting. Okay, so let's talk about some more examples of the ways in which perception is very, very relative. As a driver, you probably don't like people walking around or bicycling around, and as a pedestrian, you probably don't like drivers or people who are bicycling around. And why does that happen? Well, as a pedestrian, you're in danger from the drivers and you're not part of the driver group. And as a driver, you're in danger from the pedestrians and you're not part of their group. And so you kind of get this feeling that they don't know what they're doing because you're not part of them. It's easy to pay attention and be bothered by them. It turns out that holding a gun makes you more likely to feel other people have a weapon. It's a strange sort of perception, because you'd think that how holding a gun makes you more confident and feel like you might be more in power, but it turns out that holding a gun makes you feel like others have a weapon. A good explanation for this is that, well, it's easier to say that if you have a gun, other people have guns, just because it feels more prevalent. If you don't have a gun, it's easier to feel as though other people don't have guns because, again, they may feel less prevalent. Hills may seem less steep when people feel understood. And this one is kind of an intuitive one once you realize that feeling understood can make you feel more confident about yourself. And so if you're more confident about yourself, hills seem easier to climb. Finally, harmful actions seem more serious after listening to anger cueing music. So I think that one's a really, really obvious one. If you listen to some music that'll make you mad, then you're more likely to think that different things are more serious or more harmful because you've already kind of been put in that mind space. So be very, very aware of how your mind space, or the place that you're at mentally, or the conditions that you find yourself in, can affect the way in which you perceive different things. Let's talk about sensory adaptation. So this is very similar to habituation and sensitization. Sensory adaptation is how we get used to certain stimuli after experiencing that information. And so we start to experience things relative to the new norm. So in this case, it's not so much whether or not we feel things or don't feel things, although that does happen in this situation. Instead, it's how we perceive things in a very relative way. So imagine, this is a really fun experiment to do, and I'd love you to do it at home if you'd like. Putting your hand in hot water and another hand in cold water, and then placing both of them in kind of room temperature water. You'll notice that one hand feels cold and the other hand feels warm, and it's not that the water itself is an actually different temperature. You know that the room temperature water is the same temperature throughout the bowl. Instead, what's going on is that your cold hand got used to the cold, and so room temperature water feels relatively warm, and hot water feels relatively cold. And the reason we even use the word relatively is because the information is relative to the other information that your senses have been feeling. Okay, sights and sounds. This is the first thing that came up to my head when I thought of sights and sounds: a nice EDM concert that's about as loud and bombastic as it could possibly be. To me personally, for most of my life, something like this is terrifying because I don't really feel like I belong there, but also because I have trouble with really loud noises and bright things. That can happen depending on who you are. Maybe I just have some sort of stigma. But probably the more I would go to concerts like this, the more I would feel comfortable with it based off of that stuff we've talked about. Another thing is that I tend to feel a little bit uncomfortable with strangers in large crowds, so it may make sense that I would naturally associate negativity to concerts because I'm in that headspace. So maybe if I get used to going to concerts that are empty, maybe I could enjoy them more, or maybe if I just get used to going to concerts by going to concerts, I could enjoy them more. Or if I make sure to have a good time by going to a concert, I could enjoy it more. So this is one of those more sciencey parts that, in my opinion, is closer to physics than it is psychology, but it's good to know, and it'll be interesting in helping us understand how our vision works. Wavelengths of light. What are we talking about here? So we, you know that light is a wave, just like waves on the ocean are waves of energy. Light is a wave of energy that travels through space to hit our eyeballs so we can perceive visual information. It turns out that colors are just different varieties of wavelengths. You see here that blue tends to have a shorter wavelength, red longer, and you can also have the amplitude or the strength of the wave over here on the right, that meaning also kind of the size, the up-down extent of the wave, affects how bright a color is. So this isn't something that you necessarily need to know. It is important to know that light comes from wavelengths, and the reason that's important is because it affects the way in which we perceive that information. For example, go ahead and click on this video. It comes from, I think it was the making of a music video, or just on its own. I'm not sure exactly, but the cool thing about this is that because visual information is made of waves, and because audio information is also made of waves, we can actually visualize sound waves by allowing them to resonate with certain materials. So you may have done this if you've gone to like a kids museum at a major city, but this video does a great job of showing you how sound can have a visual component to it, because it is actually a physical thing moving through the world. As usual, I'll give you 3 seconds to click on that video. 3, 2, 1. Another example of how wavelengths affect our perception is that rainbows are actually sprays of light at different wavelengths. The way a rainbow works is that light that is all one unified wavelength gets shined through something that affects the way in which the light moves. Either a prism, or in this case a water droplet. The water droplet causes the band of light to separate into a bunch of different wavelengths, kind of in the same way that if you put your hand in front of a hose, the speed and form of the water is going to change drastically and spray out kind of in a bunch of different directions at a bunch of different rates, just depending on how it hit your hand. In the same way, light, depending on how it hits the water droplet, will spray out into all the different colors that we can perceive. The reason that we perceive all the different colors kind of in the same order every time is actually, I don't know why. I thought I did, but I just walked myself into a confusing thing. So here's a good opportunity for you. See if you can learn why do we always perceive rainbows in the same order, and can you explain how that is affected by our perceptions? Next up, wavelengths of light. So we've already talked about these wavelengths of light, but this does a good job of showing you how light actually exists in a series of a larger set of wavelengths. These are presented in terms of 4 to 700 nanometers. So a nanometer is a very, very small version of a meter, as described here. It's a billionth of a meter. So if we were small enough, we might be able to perceive that. But what's cool is that we can actually see that radiation is on this line here in terms of gamma rays and X-rays. We know that the smaller the bits of radiation, the more dangerous they can be, because they can kind of get between our DNA and hurt us that way. They can also fry our bodies, so that's no good. The wider ranges of waves, things like radar and broadcast bands, and if you go further out here, sound waves, have much, much, much wider amounts of size. And so if you think about it, at some point, these nanometers start to become waves that are physically big enough for us to perceive. Here's an interesting fact. If you put a fly in a microwave, it won't die. Why is that? Turns out that microwaves are maybe a foot or a couple of feet wide, and so they have very, very little opportunity, or maybe they're a couple inches wide. I don't remember. But microwaves, turns out, are too big to really affect the fly very much. And so that's why it kind of does that. There are videos on the internet if you want to check that out, if you want to learn more about it. But let's go ahead and move on. Okay, so here I've got a really, really wonderful video. This is not required. It kind of really goes more into evolution than psychology, but it's a wonderful video that presents the way in which the eye evolves from simple eyes that like really, really basic animals like bugs might have, up to our complicated eyes that we have. And it goes through a number of evolutionary topics. Definitely not a required video, but if you're interested in it, go ahead and give it a watch. The other thing to get out of this is the structure of our own eyeballs. You can kind of see that light goes through a lens and it gets refracted kind of in the same way that information gets refracted for a camera. And that refraction allows it to focus and become the right size for our fovea to perceive. But we have these sensors along the inside of our eyes called the rods and cones, and they're really the nerves sorry, the cells that we use to perceive that visual information. The fovea here has a higher concentration of those rods and cones, so it makes sense that we have better vision in our central point of our eyes, and we do have vision around that, but it's not quite as good or clear. And you may notice that if you try to look at things without directly looking at them, they're not in as good focus as if you directly look at it. So maybe try and mess around with your vision there for a moment. Another thing to point out here is that your eye is connected to your brain through an optic nerve. It makes sense that all of that information would have to be transmitted somehow, and it turns out that you are missing some visual information thanks to the fact that your optic nerve has to be connected somewhere, and wherever it is connected, you can't have visual sensors. So because of that, you have a blind spot, and we'll actually have an opportunity to find your blind spot and experience it in a moment here. But before we get there, let's talk about the rods and cones that I was mentioning before. So what are rods and cones? Rods are detectors of light, seen here, these longer boys. Rods are detectors of light that detect black and white and gray information. So they kind of just detect intensity of light. Rods are better at working in low light and peripheral vision situations. They're better at detecting movement, which is why it can be really easy to catch movement out of the corner of your eye. That's going to be the rod's job. Cones, on the other hand, are designed to view color. There's actually 3 different types of cones. I believe there are cones that detect blue, red, and green. And that's going to affect the way in which we perceive colors. So just to clarify, I've got a real image of those here on the right, although the colors here are not actually the colors that they are in your eye. They've just colored the things for you so you can tell which is which. Over here we have a diagram of the cells in your eyeball just to show you kind of how they work. Okay, so we've got a couple demonstrations about how our eyes work and how our perception works and things that are easy to mess with. First, on the right side here, go ahead and put your fingers so that they're both of them touching, and put them kind of at eye level. And you'll notice that as you start to move them closer and closer to your eyes kind of have to cross to see them, but you'll also notice that you might begin to see a third kind of chunk of finger to start to appear. And what's going on there is that your finger is being seen by your left and right eye. The eyes don't notice the bits that they can't see due to the fact that your fingers are too close to the eye, but they do notice the fact that they can see the finger part of it twice. And the way they interpret that is that there is a third little floating little sausage finger there, but it's not that there's an extra finger there. What's actually going on is that both of your eyes are perceiving the same information that the other one is perceiving, but just in slightly different parts of your vision, resulting in a weird image. Okay, so let's practice or try identifying your blind spot. This is how you do it. We're going to follow these instructions over here using kind of this picture, but if you like, you can click on this link to get more examples of this. Here's how we're going to find your blind spot. First, close your left eye. Second, stretch your arms out as far as they'll go in front of you and make those two L shapes. Put the L shapes together by meeting your thumbs, and then look at your left finger. Look at the point of your left finger, the tip of the left finger, using your right eye while your left eye is still closed. Then kind of wiggle your right finger around a little bit. You may need to move it up or down or left or right a little bit, but eventually you'll notice, if you look at the finger without directly looking at it, you'll notice that your finger just disappears. Why does that happen? Well, what's going on is that that is the part of your eye that has the blind spot. And why that happens? Well, remember that there are no rods and cones wherever your optic nerve is. Despite there being a blind spot in your vision, and despite it being kind of right in the middle of the front of your vision, you never really notice it. Part of the reason you never notice it is because your two eyes compensate for each other's blind spots, but another reason for that is, again, that what we see is not actually what our eyes are seeing, but instead what our brains perceive. So we'll naturally ignore that bit of no information because it's not very useful. Okay, so just like there are visual blind spots associated with the optic nerve, there are also color blind spots, and these come from the way that our eyes perceive colors. Remember that we have cones for blue, green, and red light. This is also approximately cones for short, medium, and long wavelengths, kind of shown here in this graph. Now, the way our perception of colors works is through something called opponent process theory. We don't see just blue, green, and red. We see that combinations of blue, green, and red result in different sets of colors. And so we have three sets of processes in our perception that affect how we perceive that information. First, red versus green. Makes sense that we could do that because we could compare the green cones compared to the red cones. Imagine this. When you're looking at a picture, some amount of green cones light up and some amount of red cones light up, and the quantity or the strength with which they light up, with which they activate, can tell you whether you're seeing a more green picture or a more red picture, or a picture that's somewhere in between, which turns out to be yellow. Okay, so we've covered this right-hand side of the color spectrum, but how do we perceive these other ones? Well, we know that we have blue, and we actually have another piece of opponent process theory, blue versus yellow. So we get yellow by comparing green and red, and we can get blueness by comparing the blue to that yellow. That allows us, again, to perceive blue, cyan, and green and yellow based off of the relationships between those two things. If something really has no red or yellow at all, we would perceive it as violet or purple, but there is actually some interesting things to learn about purple and violet. You can feel free to Google or go to YouTube and type in "violet is not a color," and you'll find videos that explain why. The last way that our vision works is by understanding light versus dark. So remember that we have our cones and our rods. The rods process the light versus dark information, and they'll tell us whether the color is really bright or darker. So there's opponent process theory, the idea that we perceive color or vision in general based off of comparisons of two different types of cones, or a comparison of multiple different types of rods. Does this explanation make sense to you? Part of the conclusion from this explanation is that there are certain colors that we can't see. We can see blue-green, which is kind of a cyan. We can see green-yellows and yellow-reds, but because our eyes are designed to compare green versus red, we cannot see green-reds, even though those colors do kind of exist. And because our eyes are designed to see blue versus yellow, we can't see blue yellows, even though that color does exist. Now, I just said that we can see blue yellows, and we can see blue yellows in a way. We perceive them as cyans and greens. So it turns out that we can see blue yellows, and that's kind of a mistake. But we can only perceive blue yellows as greens or cyans, like I said. So that's why there's no such thing as a greenish red. Does that make sense? I kind of talked myself into a bit of a circle that was a little nonsensical, but I hope it makes sense for you. Okay, so this is about halfway through the slides. We're at about 50 minutes here. So I'm going to go ahead and pause, upload this for today, and catch up with the rest of the material in a moment. We don't have that much for the rest of the material. A lot of it are cool visual illusions and stuff, so the next video should be a little bit shorter and more fun. This is Gabriel Sines, signing off for now.